has already connected, so we can start. Good morning to everybody here in Israel this morning, and welcome to the next ACRC virtual webinar. And today we have an honor to host Professor Massimo Alioto. A short intro for Professor Massimo Alioto. Professor Alioto is a professor at the ECE department of the National University of Singapore, where he leads the Green IC group and is the director of the Integrated Circuits and Embedded Systems area and the FD Fabrics Researcher Center of Intelligent and Connected Systems. He held positions at the University of Siena, Intel Labs CRL, University of Michigan, Ann Arbor, and University of California, Berkeley, EPFL, Lausanne in Switzerland. He's co-author of 300 publications on journals and conferences and 4 books with Springer. And his primary research interests include ultra-low power circuits and systems, self-powered integrated systems, near-threshold circuits for green computing, widely energy scalable integrated systems, circuits for machine intelligence, hardware security, and emerging technologies. Professor Alioto is the editor-in-chief of the IEEE Transactions on VLSI Systems, distinguished lecturer for the IEEE Solid State Circuit Society, and was deputy editor-in-chief of the IEEE Journal on Emerging and Selected Topics in Circuits and Systems. Previously, Professor Alioto was the chair of the VLSI Systems and Applications Technical Committee of the IEEE Circuits and Systems Society. So, Professor Massimo Alioto, we are honored to host you in our ACRC virtual conference, virtual workshop, sorry, and we hope to host you soon in Israel in a face-to-face once this COVID ordeal will be over and behind of us. So, the stage is all yours, please.
Very good. Thank you very much for your kind introduction. And indeed, actually, it was one of the goals of last year to actually visit in presence. But then you know the story, what happened at the beginning of the year. So yeah. I guess that the virtual gatherings are the best that we can do these days. And hopefully we'll make the most of this hour and a half we'll spend together. And the main topic that we'll discuss today will be about some recent advances on systems as well as architectures with ultra-wide power performance adaptation that exceeds by orders of magnitude what is traditionally allowed by voltage scaling. So this is the outline of my presentation. We'll start from the power performance trade-off in energy autonomous integrated systems, and we will see that actually, the design targets are multiple and they need to be pursued, although at different times, all of them during the lifetime of a device. And we'll also discover that pure VDD scaling, traditional voltage scaling, even if in its ultra-wide version, is not enough. And then we'll start talking about what allows us to exceed the power performance trade-off and the space that can be explored with voltage scaling, and how to exceed it through adaptation in both the clock path and the data path of digital subsystems. And then we'll look into how to expand the trade-off towards the other hand, which is minimum power consumption, essentially making the power consumption compliant with the power budget offered by today's harvesters without any support of the battery. And then I will wrap up. Well, by the way, I would like to share with you that having scheduled an hour of conversation, this will be mostly about building blocks, and there is a follow-up talks. Maybe, hopefully, this will be the follow-up in the physical version at Technion instead of the virtual version today, which is more about architectures and computing frameworks. So general purpose processors, how to apply these general concepts to processors, as well as broad purpose in-memory computing engines that exceed the traditional neural network capabilities of conventional and even recent in-memory compute frameworks, as well as energy quality scaling for the enhancement of the energy efficiency and throughput of AI in AI applications. So that's probably the follow-up. Right now, we'll focus on the topic of this conversation, this talk, which is about energy autonomous integrated systems and how to expand their power performance trade-off. Well, first of all, I would like to start from the context. So we are talking about energy autonomous systems that are at the physical interface of the Internet of Things. So these are sensor nodes, and as we all know, sensor nodes are actually becoming quite intelligent. So they are able to not only perform event detection, they are also able to perform some reasonable level of data analytics on chip before they communicate with the cloud. And this is necessary for many reasons. One is certainly the power consumption related to wireless communications. So sending raw data is very expensive from a power perspective, but there are other reasons that are related to the data deluge issue and challenge that the proliferation of IoT devices is posing in all our wireless networks. So we'll focus on IoT nodes, which is the physical interface, as I mentioned, to the physical world. Now, in any of those sensor nodes and in general energy autonomous systems, the main constraints are actually dictated by the energy source. And the energy source is typically composite. It's a hierarchy of components that typically comprise energy harvesters and a battery at least, and or a supercapacitor. And the reason why we do that is to combine the appealing properties of each of those categories. In particular, the high power density of batteries and supercapacitors with the high energy density of energy harvesters. So we basically combine the best of the two worlds to have a better and more capable energy source with higher energy density and power density. And depending on the composition of the energy source, the energy and power constraints at the system level are different. In particular, if it's a purely battery-powered system, which is mostly what conventional and most of commercial systems are, the most important parameter from a power management point of view is really the average power, because this dictates the rate at which the battery is discharged, and ultimately this defines the lifetime, the battery life of the system. Then we can have hybrid energy sources where we combine batteries as well as energy harvesters and maybe even supercapacitors. And the presence of the harvester essentially reduces the effective power that is drawn from the system, from the energy source. And if the average harvested power is equal or higher than the average system power, then the life of the system can be in principle, nearly perpetual. It means it translates to decades of battery life. Then we have a third and very important class of systems that have gained a lot of interest in the last 5+ years, and this is purely harvested. So there is no energy storage. So the peak power is really what determines the ability of the system to operate or not. So as long as the power of the system, the peak power, is within the instantaneously delivered power of the harvester, the system can keep operating without any interruption. And then there is an even more recent class of systems, which is called battery indifferent. And in that case, this class of systems is able to operate as a battery power system as long as there is enough energy in the battery. And whenever the battery is depleted, it's running out of energy, then its power can be reduced dynamically to a major extent so that its consumption is able to be below the instantaneous power consumption delivered by the harvester. So here, what is particularly interesting is that this framework can be used by systems that are particularly compact, so millimeter scale, in which the battery is typically very small and has a capacity of probably tens of microamp hour, so it will be depleted very frequently. So this framework, the battery indifferent framework, allows the system to keep functioning even if the battery is depleted, which will be frequently because of its small capacity. And the interesting thing is that the harvester will supply the power that is needed by the system, or vice versa. The system is able to scale down its power so that it will keep going even under the very limited power provided by the harvester. Now, typically the type of power targets that are necessary for multi-year operation of systems, energy autonomous systems for battery powered systems, is in the order of microwatts and sub-microwatt if you want to really reach the decade scale, decade long. But if you want to last long, let's say for more than a decade, and you want to also be able to use miniaturized batteries, for example, solid state batteries that are millimeter scale and die size. So these are actually on a silicon substrate. These are commercially available and they can be stacked up and processed like any other silicon die. Well, in that case, their lifetime is in the order of hours. So it's not very long. So it means that you will need a harvester anyway. And classically, whenever the active power of the system needs to be reduced, it's well known that duty cycling helps on that because operating in sleep mode for most of the time and reducing and restricting operation active mode only for short periods of time reduces the average power of the system by an extent that is dictated by the duty cycle. So the smaller it is, the lower the average power will be. And in both cases, so regardless of whether you're considering the always-on block or the duty cycle block or subsystem, it doesn't matter. Voltage scaling always helps reducing both the energy and the power. Now, the question that we would like to discuss about and answer in this talk is the answer needs to be found in the appropriate context, so in applications. So as we all know, next generation IoT devices will be event driven. And this means that they will be constantly on, always on. At the same time, they will be able to detect events. For example, this is a speech recognition system. In this case, you don't really want to have speech recognition engine running all the time. This is very power hungry. So you will have a front end that determines whether there is speech or no speech. So if there is no speech, the speech recognition engine is kept off. Otherwise, it's turned on whenever there is voice activity. So this means that event-driven systems need to actually occasionally, whenever an event is occurring, to scale up very substantially their compute ability to perform data analytics on the incoming samples. For example, in the speech recognition system example, you want to move from mere simple voice activity detection to full speech recognition within the same accelerator. And this takes a tremendous increase in performance. So essentially, what we want to do is to keep the energy low in the common case. So this is event monitoring. But whenever needed, so whenever an event is occurring, you want to scale up the performance, usually by scaling up the voltage to the nominal voltage. But that's not enough, actually, in practical applications. You want to exceed this capability. And there is another limitation of voltage scaling that needs to be observed. And this problem is related to systems that are operating constantly or occasionally in purely harvested mode. For example, in different systems, this happens only when the battery is running out of energy. In purely harvested systems, this happens continuously. So in this purely harvested mode, then you actually need to consume as a system a power consumption that is below the instantaneously available harvested power. Well, that's pretty small. Just to give you a sense, if you look through the classical principles for harvesting, so light, vibration, thermal, and so on and so forth, typically the harvested power is in the order of nanowatts to tens of nanowatts for millimeter scale harvesters. Well, that's not very much power. Because, for example, if you want to provide power to a simple ARM Cortex-M0 microcontroller, which is a pretty standard component in any IoT commercial device, so this means about 100 kilogates for a reasonably simple configuration. So nanowatts translates into a power consumption of 0.1 picowatts per gate, per logic gate. That's a very small number. Typically, 2 orders of magnitude lower than the leakage that is allowed by HVT transistors in any practical technology. So this means that a harvester in the millimeter scale is not even able to support the leakage of the microcontroller unit, not even to mention the whole system. So it means that if you want to keep functioning and having the MCU, the microcontroller unit, continue to operate even under this tiny power budget, there is only one option. Its power consumption has to be well below leakage, or what we call sub-leakage power consumption. And this can actually be achieved, and there are different ways to do it. So this has been proved experimentally, and many things are actually happening in the field, which I will share with you in the next few slides. So overall, when we design next generation IoT devices that are energy autonomous and long-lived and in the millimeter scale, you don't really want to pursue a single design target, which is classically minimum energy. No, this is not enough. You also need to scale up performance upon the occurrence of events at the same time. If there is a power event, for example, in a battery indifferent system, the battery is being depleted, is not available currently. In that case, that's a power outage. That power event needs to trigger a third design target, which is minimum power. It means sub-leakage power. So how do we pursue this very wide range of power performance trade-offs that are well beyond voltage scaling, as I will show in the next few slides? Well, we need to introduce some innovation, and that's what we are going to talk about in the rest of this, this speech. We'll start from the very first objective, which is pretty simple, and so I'm going to spend probably a minute or so. So this has been design target that has been explored in the last probably 10 to 15 years. So that's a very well understood design trade-off. So I will just mention the principles that have been explored and what the challenges are. But this is a fundamentally solved problem today. So first of all, we all know that a voltage scaling allows to reduce voltage down to the so-called minimum energy point. And operation at the minimum energy point is somewhat problematic for a few different reasons. The first one is the fact that process voltage and temperature variations, as well as the effect of aging, actually becomes more significant. It means that you need to add a timing margin that can be easily comparable to the nominal clock cycle. It means that it might not be even useful to operate at minimum energy point if you have to margin for all these different contributions to the whole variation in the clock cycle, in the timing constraints. So we need to actually reduce this margin in different ways. The first is, of course, using variation-aware design. This is mandatory. And by the way, in all this, the subsequent slides, you will see that sometimes I will refer to specific publications on research work that we have carried out to answer and address the related challenges. So variation our design, you might be interested in exploring this publication of a couple of years ago that introduces a framework that that allows designers to tackle the variation issues with really back of an envelope calculations on a piece of paper. Which we believe can be quite beneficial for designers that want to quickly explore the design space, including the effect of variations. And of course, there is a whole literature which we have contributed to in terms of error detection and correction for margin elimination at runtime. And there are also other aspects related to energy reduction and minimum energy pursuit, which is related to data movement. So data locality enforcement is certainly easier to pursue whenever we consider in-memory compute frameworks. For example, this one, which we published recently, to enable for the first time broad purpose operations. So not just neural network computations, but also classical, traditional DSP computations that are actually necessary whenever we perform neural computations on a signal. Before you perform neural network recognition tasks, you really need to precondition the signal, which means DSP. So these techniques that we have proposed allow us to precondition the signal within the same memory without having the signal to be accessed, the memory to be accessed from outside. So the memory stays within the memory and is then preconditioned. And whenever there is an event, then the neural network task is again executed on the same memory. So no data in, no data out. Feel free to explore. And then we'll focus now on something that is, it's a challenge that has been more recently tackled, and that's still an open problem. So there are solutions, but the game is not, it's not over. Actually, we have to keep innovating to enable more capabilities in this domain. So how to scale up performance or further reduce the minimum energy point dynamically whenever we scale the voltage up and down. Well, we'll start introducing the problem from a very general perspective. So in general, we want to explore certainly wide voltage scaling, where transistors operate from weak inversion to strong inversion. So the underlying design trade-offs are very different from a single or narrow voltage scaling. And this translates typically in a performance degradation when you push down to the minimum energy point by a couple of tenths of X, and you typically have, let's say, an order of magnitude energy reduction. Well, the problem across this wide voltage range, wide voltage scaling, is that there are actually trade-offs that are very sensitive to the voltage. In particular, when you look at the clock network, you have a clock tree structure where the number of repeaters that are inserted in the clock network is highly dependent on the voltage, operating voltage. But if you're scaling the voltage up and down, then any fixed design, clock network design, is suboptimal. So it will make the design less energy efficient and also more prone to robustness issues, clock skew, to be more precise. So you need some flexibility to actually adapt the structure of the clock network to the very voltage, operating voltage that you are adopting at any point of time. And similar considerations hold in terms of microarchitecture. So microarchitectures, actually the energy optimal microarchitectures, are highly dependent on the voltage, adopted voltage. So if you are exploring a wide range, you actually need also flexibility at the microarchitectural level, which is what we are going to discuss next. By the way, again, feel free to explore some of the publications we have in this domain to explore and to go deeper into these solutions. Well, clock networks. Usually, you might want to design for performance, let's say nominal voltage, But the problem with this, and in this case, since at maximum nominal voltage, maximum performance, the wire delay is significant compared to the gate delay, you want to have what we call deep clock networks. So you want to have many repeaters along the way from the clock root to the leaves of the clock tree. But the problem of having many repeaters is that at lower voltages, the clock skew will go up. Simply because actually at lower voltages, you don't really need as many repeaters, clock repeaters, simply because the wire delay now is being a smaller fraction of the gate delay, because the gate delay at lower voltages is just becoming larger. So in that case, you want to move from deep clock networks to shallow clock networks. Well, in this case, if you start designing a shallow clock network at low voltage, and then you scale out the voltage dynamically, well, again, you will need actually more clock repeaters at higher voltages. So it means that the clock skew will go up. So essentially, there's no single clock network that can satisfy and optimally handle the energy clock skew trade-off across all voltages. So you need reconfiguration, which is what we are going to talk about now. Well, reconfigurable clock networks, and you can refer to this JSSC paper published in 2019, is a clock network where each clock repeater is bypassable. It can operate normally, or it can be bypassed. So it's like not having any clock repeater between one wire and the next one within the clock network. And at nominal voltage, you want to have the maximum number of clock repeaters. So this is essentially deep clock network. So all of them are operating in normal mode. On the other hand of the spectrum of the voltage range, you want to operate with bypassed clock repeaters. So they are bypassed, so it's like skipping them. So now you have a shallow clock network, and you can adapt to the specific voltage, operating voltage. Well, this can be done very easily by replacing classical repeaters with reconfigurable repeaters, where in normal mode, they're operating just normally, but in bypass mode, they are just bypassed by a pass transistor. The interesting thing is that bypassing will occur only at low supply voltages. So it means that if you actually set the gate voltage of the pass transistor at nominal voltage, which is typically available in the chip anyway before the down conversion to the lower voltages, in that case, this pass transistor is inherently gate boosted. So it's experiencing the maximum gate voltage. It means that it's actually much stronger than all other neighboring transistors. It means that even if it's a small transistor, you don't need to increase its size to make it strong enough to make its equivalent resistance much smaller than the equivalent resistance of the neighboring transistors and wires. And this mechanism, of course, since it's tracking the operating voltage, it needs to be integrated with the existing dynamic voltage frequency scaling, DVFS, frameworks. And this is done very easily by adding a third column to the lookup table that traditionally expresses the clock frequency as a function of the voltage, which is defined in turn by the power mode. So what you need to do is just to add a third column that will specify which clock repeaters will be bypassed for different voltages. So it means that the inclusion of reconfigurable clock networks in runtime DVFS frameworks is actually trivial to do. And I will probably skip this, and I will focus on the gains. So the measured clock skew in an FFT accelerator with about 500 kilogates complexity is more than 3x across voltages. It means that now you can keep actually the clock skew nearly constant when normalized to the gate delay across all voltages. And this translates into two main improvements. Well, the first one is that you're going to reduce clock skew at lower voltages. It means that you are now reducing the minimum operating voltage, because hold violations will be mitigated because the clock skew is now reduced, right? And in the silicon prototype that I mentioned a minute ago, Vmin was reduced by more than 100 millivolts. Well, this means robustness or yield, right? Typically by a factor of, we have observed by a factor that restores the yield to the typical values that would be expected at nominal voltage. Now, this reduction in Vmin offers a few interesting opportunities. Well, the first, actually, simply because you have reduced the clock skew, the performance goes up at lower voltages, but that's not really a major advantage. What is really interesting is that you're able to reduce the energy by 1.4x simply because you're operating now at a lower voltage, lower Vmin. So that's the main advantage. So we can further reduce the minimum energy point because we can reach it now at yield. And the same concept can actually be generalized to microarchitectures. So if you have a microarchitecture and you're exploring different options, actually we all know that the choice of the logic depth, so the amount of logic that you have in each pipe stage, will dictate the trade-off between leakage power as well as clocking power and dynamic power from the combinational logic, right? Well, in that case, you have a trade-off and an optimal choice for the logic depth. So you will have, again, a minimum energy point. By the way, this is not at all related to voltage scaling. This is in the macroarchitectural domain. So this is logic depth, not voltage. So you have a minimum energy point because for very large logic depths, you will have such a slow system that the leakage energy, which is proportional to the clock cycle, will be so large that the overall system energy is actually increased compared to the minimum. And on the other hand, if you instead adopt a very small and excessively short logic depth, it means that you have many registers in the pipeline. And that means that the clocking power or clocking energy will go up. So the minimum energy point is really the trade-off, the result of the trade-off between leakage energy and clocking energy. And again, what you want to do is to adapt the logic depth to the different voltages adopted from minimum energy point to nominal voltage. How to do this? Well, you can actually reuse the same high-level concept that I mentioned before, which is reconfigurable logic depth. Essentially, you will have registers that are bypassable. When you want to have the shortest logic depth, you will not bypass them. Okay, so they will operate in normal mode, blue in this figure. Then, if you want to instead merge two neighboring pipe stages into one, you want to use the bypass configuration, where the flip-flop will actually, or the register will be bypassed by a simple multiplexer. By the way, this is just as an exemplification. You can actually achieve the same mechanism in many different ways and even more efficient than this, but this gives you an idea on at least the low-hanging fruit, what you can do first. And we are exploring other opportunities, as I will mention later on in this presentation. Now, if you have a reconfigurable microarchitecture, again, you need to adapt it to the specific voltage that you want to pursue. In particular, as we did for the reconfigurable clock networks, you want to specify for each voltage the corresponding configuration of the bypassable registers so that they will minimize the energy for every single power mode, for every single voltage. So typically, if you are comparing at ISO throughput, you're going to have a higher or a deeper pipeline for higher voltages. So let's say above threshold voltages, and shallow instead for near threshold voltages. And this is just a configuration that can be stored by enhancing the lookup table that I mentioned before. So again, including this at runtime is pretty simple. It can be integrated in full with the existing dynamic voltage frequency scaling frameworks. And this is just one of the test chips that we presented in JSSC. This is a 256-point FFT accelerator. And as you can see, the clock frequency, actually clock cycle in the shallow configuration is about twice the one in the deep configuration, as you would expect. So you basically are merging two neighboring pipe stages or not, you are keeping them separate. And the energy benefits, as you would expect, will show up both at above threshold voltages. So whenever high throughputs are pursued, as well as near threshold voltages when nearly minimum energy operation is being pursued. In both cases, I would emphasize both cases, you would get about 30% energy improvement, both at higher throughputs as well as lower energy targets. So the reconfiguration gives you the ability to pursue energy efficiency in both ranges. So you don't need to choose a design time. And of course, nothing comes for free. So the area is increased by the presence of the extra reconfiguration, including multiplexers and registers that are bypassed. And this is a little more than 3%. And by the way, as you know, FFTs are typically, and certainly in this case, register dominated. So in other practical cases, use cases, you would see area overhead smaller than that because the number of registers that are being reconfigured is actually smaller. And as another interesting capability that is enabled by this pipeline level reconfiguration is that if you combine the two curves for the two configurations for the registers and you take the best, so if you reconfigure a runtime, you're actually able to achieve an overall curve, which is this black one, which is pretty flat around in terms of energy with respect to the minimum energy point. So this means that if you're able to reconfigure now, you don't really need to tune up the supply voltage very accurately. You have a window of easily 50 millivolts, as you can see, with an energy that is essentially the same as the very minimum energy point, even if you are not setting the voltage, the supply voltage very precisely. So this also entails further simplifications and energy and design effort gains at the system level whenever you're designing the power management unit. And all these techniques actually have been developed in our lab with the support of commercial CAD tools. So everything that you are seeing is purely automated. So we have built actually automated design methodologies that have been demonstrated in previous publications. You can probably see at least two at the bottom of this slide and are now publicly available. So if you're interested in playing with these techniques in a way that is fully automated, push button by just reusing commercial CAD tools, feel free to actually just scan this QR code and go to GitHub. So you will find plenty of materials delivered by our team to let you play with the reconfigurable microarchitectures and pipelines. And feel free to reach out if you're interested in knowing more about those. We are very keen to share. We hope that this will really help our community to ambitiously improve the energy performance trade-off and power performance trade-off of digital systems. And this is digital. So now let's go wider and let us pursue an even more aggressive design target, which is what we call minimum power. It means being able to reduce the power below the instantaneous power provided by harvesters. That's very tiny. So under fluctuations of the environmental conditions, this can easily go down to nanowatts in millimeter scaled harvesters, as I mentioned before. So how to do that? I remind you that this means sub-leakage power consumption. That's actually not very complicated to achieve. First of all, let me just present the framework and what is missing, and then we'll connect the dots and see how to do it. So if you actually apply conventional voltage scaling, as you can see, you will have an energy per cycle that goes down to the minimum energy point, right? And the power consumption of typical microcontroller units or processors that is in the order of, let's say, micro level or so, okay? Well, that's far higher than the power that can be delivered by harvesters whenever the environmental conditions are not more than optimal, right? More than ideal. Well, there is a second option, which is using completely different logic styles. For example, what is called leakage subtraction logic, or dynamic leakage suppression logic, that allows to reduce the power per gate to well below 0.1 picowatts per gate. That's exactly what we want. For typical microcontrollers, it means that you can go down to the nanowatt level. Well, the problem with these logic styles is that those are confined to a very narrow range of power and, unfortunately, performance. So they're stuck to the hertz range. So even if you have more power from the battery or a harvester, you can't really take advantage of it. It's lost, basically. It's unusable. So what you really want to do is to have the ability to go to maximum performance like voltage scaling, minimum energy like voltage scaling, and then going even lower power down to nano level, while filling the entire gap by covering all possible intermediate power performance trade-offs, so that you'll be able to run at the maximum performance that is allowed by the available power budget instantaneously. Okay, well, this requires basically to adopt two different logic styles. One is CMOS, traditional standard CMOS, which is able to be fast and minimum energy. But on the other hand, you want to also have the ability to minimize the power per gate down to the sub 0.1 picowatt per gate level, so that the entire microcontroller will be nanowatt level. And as I mentioned before, there are a couple of logic styles that actually allow that. For example, dynamic leakage suppression logic that was proposed by Q. Levan years ago, and then demonstrated on silicon by the University of Michigan. What we are going to discuss next is how to get the best of the two worlds. How do you combine the capabilities of these two separate logic styles? Well, the answer is you introduce a new type of logic, which is called dual-mode logic, which we introduced at IEEE a few years ago. And this combines actually both logic styles. In particular, whenever these transistors, the blue transistors, are kept on, in particular this one and this one, if these are on, the voltage, this node will be about VDD, and this node will be about ground. Well, this is exactly how standard CMOS logic works. So it means that you're able to operate like standard CMOS logic. So you're going to be able to scale up the performance as well as to pursue minimum energy. At the same time, or actually alternatively, if you instead turn those transistors off, so the transistors in green are turned off, well, the remaining logic, as you can see here, looks like something that is also well known, which is the DLS logic with the minimum power operation ability. So in a nutshell, turning on or off these transistors, or even modulating the gate voltage of these two transistors, allows you to cover all possible power performance trade-offs from standard CMOS logic down to DLS logic. Now we can go from maximum performance to minimum energy to minimum power. And by the way, continuously, you can choose the trade-off at runtime. Now, to move on, this translates into a couple of interesting results. The first is that if you compare dual mode logic microprocessors compared to the very state-of-the-art summarized in this plot, you see that dual mode logic is the only one that is able to cover 6 orders of magnitude in terms of power and performance. So it has an unprecedented dynamic range, and it's still able to pursue nanowatt level power consumption in reasonably simple microcontroller units here. This is an MSP 430. And by the way, just to summarize, essentially voltage scaling brought us to 2 to 3 orders of magnitude reduction in power. Then if you add the pipeline reconfiguration, this buys another order of magnitude or so. And then if you further add dual mode logic in terms of circuit technique, you buy another almost 2 orders of magnitude. That's how you get to 6 orders of magnitude. Well, now, actually, we have talked about digital. Actually, we don't need to stick to digital. The same concepts apply to different subsystems. For example, sensor interfaces. Well, sensor interfaces are problematic because typically the power consumption, the minimum power consumption of sensor interfaces is lower bounded by bias currents and other always-on blocks, right? So what you want to do instead is to remove this rigid minimum power or power floor to actually have consistent, or as we name it, coordinated power scaling along with the digital subsystem. Basically, whenever you're scaling down the power consumption of the digital subsystem, you also want the analog subsystem to keep scaling its power coordinately, right? So jointly, so that none of those will actually be the power bottleneck at the system level. And the same consideration needs to apply to speed. So you don't want any of those to be the bottleneck. So to impose a rigid limit in terms of power and performance. So we introduced the concept of coordinated power scaling in removing the power floor of analog sensor interfaces by introducing and demonstrating the concept with an architecture with the 4 sensors. It's a multi-sensor architecture that, by the way, is also able to operate with a Vmin of down to 0.3 volts. So this means that if you have, for example, a solar cell, you don't even need an intermediate DC-DC converter to connect the solar cell to the system. You can just connect the solar cell directly to the system itself. So this reduces the power floor even further because you're eliminating the classical, the conventional intermediate DC-DC converters. And it has, by the way, also coordinated power performance scaling. I will skip the details on this, and you can refer to this publication from last year from JSSC for the details. So what I would like to share is that if you do this, again, if you put together the sensor interface, the underlying power management, and the microcontroller unit, now you have a pretty thorough system. Again, you get nearly 6 orders of magnitude power performance straight off. So you can still get to up to 2.4 mega samples per second, which is a pretty decent speed for this kind of sensor nodes, while reducing the power consumption of the sensor node down to a nanowatt level, in particular 3.1 nanowatts, as we measured in our test tubes. And this enables a quite interesting capability. So having a dynamic range of more than 5 orders of magnitude, you can scale down the power consumption of the system to keep operating under the power budget allowed by the solar cell down to 1,000 luxes, 100 luxes. So this is indoor light, okay? So this is quite dim indoor light. And then you go down to tens of luxes. So we're talking about late sunset, and then 10 lux, that's pretty dark environment, down to 1 lux, when 1 lux is moonlight. So yes, the system is able to continuously, uninterruptedly operate, even if the harvester, which is a commercial solar cell, which is 4 by 4 millimeters, even if the environmental condition, the light condition goes down to moonlight. So this means a simple message, which is one of the things that I would like you to retain from this talk, hopefully. Conventionally, always on and purely harvested are in contradiction with each other. If it's always on, it can't be harvested, because whenever the environmental conditions fluctuate and go down to a level below the minimum allowed by the system will stop working. Instead, in this case, we have moved the power floor of the system down to a level that is so low that even if the light intensity is extremely low, the system will keep working. So in a nutshell, the system is able to operate continuously under any practical light condition. And this is the demo. I'm sure whenever the time and the world will allow, you're all invited and to come to our lab and visit. Our lab is really open door. Feel free to come. Right now, you will have to probably live with the virtual demo, which I will do very quickly. I will not really waste your time. And this is what you can see whenever you go to moonlight. So this is 1 lux measured by the light meter. And as you can see, the system is still working. If you're curious, you can just explore the demo of our system by scanning the QR code that you have on the right of the slide. So hope you enjoy. So this is, of course, just one piece of the work on the minimum power and wide dynamic power performance scaling, well beyond voltage scaling. And this includes also other components, for example, amplifiers, published a couple of months ago, digital to analog converters, analog to digital converters, as well as wake-up oscillators. This is all nanowatt or deep sub-nanowatt stuff. Voltage reference, so picowatt, as well as other sensor interfaces. The latest one has actually been just presented at IEEE about 10 days ago. So just feel free to go through the proceedings of IEEE. You will find the related details. And overall, communications remain the latest piece of the complete system to be demonstrated. And for pre-publication policies, I'm not really able to share with you more details today, but I can tell you if you visit our lab, we actually have not publicly disclosed, but demonstrated experimentally now wireless interfaces that are able to communicate wirelessly in the 10-meter range within the target power. So what we have said so far, what we have seen so far, will be publicly shared and demonstrated soon to be also allowed, including communications, wireless communications. So just bear with me for a couple of months, and then we'll be able to share it more in detail. And eventually this boils down to widely scalable systems with wide power performance scaling. So normally, you want to minimize the energy per operation. When interesting events are occurring on signals, incoming signals, you want to scale up performance to perform data analytics to analyze the incoming data in near real time. And this requires upscaling of the performance. Then if there is a power event, not signal, but power events, for example, the battery now is running out of energy, so it's a battery-driven event, then you want to keep operating at lower performance, of course, according to the available harvested power. And then eventually, if there is a glitch in the harvested power that temporarily actually provides even lower power, then you want to have another design target that allows you to prevent and preserve the information that has been stored in the memory and then recover whenever the harvested power goes back up to nanowatts. And we believe, although we will not talk about this in this talk, that embedded memories will actually make a big difference in demonstrating this thorough power management framework that exceeds by orders of magnitude the capabilities of conventional voltage scaling. So now, it's not cartoon time, but that's the end of our talk. So I would like to wrap up and summarize what we have discussed today. The takeaways. First of all, we have observed that in next generation energy autonomous systems, it's not true that pursuing minimum energy is sufficient. No, we need to pursue actually very different design trade-offs and adapt to the instantaneous power availability as well. Minimum energy, maximum performance, minimum power. The exploration and the coverage of this power performance trade-offs is allowed by techniques that introduce enough flexibility and reconfiguration at the circuit and gate level and microarchitectural level of abstraction in the clock path and the data path. Then we also discussed that on the other hand of the power spectrum, we need to pursue sub-leakage consumption, and this requires the adoption of alternative logic styles that are able to function like CMOS logic normally, but if the energy of the battery is missing, is not really there, then you want to comply with the power provided by the harvester, which means sub-leakage consumption. And then to further reduce the system power floor, you want to remove as much as possible rigid power contributions. So you want to get rid of bias currents, or at least you want to make them widely scalable. And you want to also remove DC-DC conversion stages that are not essential to further reduce the power floor. So overall, I believe that these capabilities allow systems to be more intelligent because we can actually scale up intelligence and performance occasionally while still keeping their average power lower than what allowed by traditional voltage scaling. But as a byproduct of it, actually, you can see that the ability to switch from battery operation to pure harvesting allows the adoption of batteries that are much smaller in size, much smaller capacity, because now they don't need to support the system for long periods of time. It's okay if they actually run out of energy frequently, and then they go back up to allow faster operation when needed. So in a way, shrinking batteries to this extent, so this means 2 to 3 orders of magnitude, means that we are going to use much less lithium and batteries much more judiciously than we do today. And that's pretty much necessary if we think that the IoT will ultimately require about 1 trillion batteries, which is an enormous number. Well, this enormous number has a very significant impact in perspective on the planet, and it's actually the health of our planet. So I believe that this work, apart from enabling new capabilities, will also allow to shrink batteries and reduce by orders of magnitude the consumption of lithium extraction and then the disposal of batteries. So it will eventually make our planet a little greener too, and that's very important to us as well. More and beyond the research aspects of it, this is an idea that we are pursuing very actively to hopefully make our planet not only smarter but also greener. And just 10 seconds to thank my students and the researchers in our group. It's just a lot of fun to work with them and to explore new things. And if you're interested, just go to our website to see what's going on, what we are doing these days. And you can dig deeper in the literature in special issues that we have led, so TCAS-I and JetCAS, as well as books that was presented actually at last ISSCC last year. This is for power performance scaling beyond wide voltage scaling. Another book that was released at ISSCC 2 years earlier. This is the first book on IC design for IoT. And also a book that will be published soon, so stay tuned. Hopefully this will keep you, this will keep some suspense, will make the publication of this book more interesting to you, so just stay tuned. And also there will be another edition of the mid-course on energy constrained integrated systems. We all know what mid-courses are, with solid-state circuits leaders in their fields, so great speakers, as you can see. Stay tuned for the upcoming 2021 Asia edition for the end of the year. So what we hope is that by that time, the world will be kind of back to normal or so, thanks to vaccines and other measures, so that we'll be able to actually see each other in person. Thank you very much for your attention. I will be more than happy to take your questions now. Thank you.
Thank you, Massimo. Thank you very much. We have a few questions in the chat, and as usually, people can raise their hands and unmute themselves, by the way. So the first question was from Tahi Burke. Are you assuming rechargeable batteries? Tahi, would you like to ask the question by yourself?
Yeah, sure. I guess you weren't referring to lithium button cell types, but rather to ones that you can put energy into as well, because you say that they drain and then refill, right?
Correct. Yes. So okay. The underlying assumption throughout the entire talk is that whenever we have a battery, since we are pursuing aggressive miniaturization, no single battery can really last for 10 or 20 years if you want to keep the system going all the time. You have to sleep most of the time if you want to do that. But if you want to keep the system always on, then you need to have, and you want to maintain, to keep the form factor within the millimeter scale, then you really need to replenish the battery on a regular basis. So it means that you need harvesting as well as rechargeable batteries. Well, the good news is that actually the type of batteries that are suitable for these applications, and those are basically solid state batteries, those are not only miniaturized, but they also they are very low cost. So they are perfectly suited for these applications. They actually have probably the lowest cost across the entire spectrum of commercial batteries. But on top of that, they actually have the longest shelf life, which means that you actually can have a 20-year life for the entire system, because this is not limited by the shelf life of batteries. If you consider any other type of batteries, they will not reach this long shelf life. So all these factors actually fit nicely with each other. So that's why I believe that the only way to get there is to have rechargeable batteries. And by the way, not any battery. I'm referring specifically to solid state batteries. And there are multiple vendors these days that these are widely accessible commercially.
Yeah, by the way, regarding the amount of lithium, if you take the car batteries, all the stuff you're talking about, even with trillions, is negligible. Because a 64 kilowatt hour car battery like in mine is equivalent to many batteries of the type.
If you don't mind, I will challenge you, because I have done the math.
Okay.
So I have not presented, but basically, okay, I will keep it simple. And then maybe if you're interested, I'm very passionate about this, so we can have another talk. Basically, to summarize, and now I will mention something that is of public domain, so that I will not need to make up anything. So if you refer to the talk that was given by Rob Aitken, for example, at the ARM yearly event, I think it was last year, he calculated, and I did the math, so that is actually right. So if you want to have a coin cell battery for 1 trillion devices, you need to extract lithium for 3 full capacity years. It means that apart from, even without comparing with other sectors, which I understand, so electric vehicles, sure. But because of the scale of the IoT, so we are going at trillions, not tens of millions.
Yeah.
Then the overall amount of lithium would take 3 years of full capacity extraction. So it means that you will need to stop extracting lithium for 3 years for any other application. And by the way, if you also look into, this is something, some calculations that I did some time ago. If you want to replace batteries every 5 years, so we are assuming a pretty good battery life according to today's standards. If you want to replace batteries every 5 years in 1 trillion batteries, 1 trillion devices, this takes assuming a cost per battery replacement in the order of $20, which is what all market reports agree on, this means $4 trillion a year. So there are reasons that are strictly environmental, and there are also economical reasons that don't really allow us to have 1 trillion batteries, at least of the size that we are used to today. So the main point that I would make here is that,
this I agree.
So first of all, we need to shrink batteries first. It means we have to design systems that will be able to survive even if they are depleted frequently, and they are then recharged, so you will recover the ability to use that energy. And more longer term, you also want to actually remove batteries as much as possible. That's a longer term objective that we are pursuing, and that includes actually what I mentioned before, which is communications, which is probably the most debatable subsystem across all of those that we have dealt with today. I hope that this gives you at least a sense of our take on this.
Okay, thanks.
Yeah, you're welcome. Thanks for the question. Very good, actually.
Yes, my question, thank you for a very interesting lecture. You use in your many designs very low, even extreme voltages. My question is whether the foundries support you, which means do they qualify the cells, standard cells using such low voltages? And if not, how do you think we can adapt your technique in mass production?
Thank you for the very good question. First of all, I have to clarify that if you're talking about the latest part of the talk where we got down to nanowatts, dual mode logic is actually patented technology. We patented some time ago, so it's not available from foundries, okay? But you can integrate them with commercial design tools. So you can build, and we have built, completely automated design flows, okay? So the design aspect is not really a challenge. We actually have solved it. The challenge you have mentioned is still open. So in our test chips, actually, but of course we have not qualified these techniques for mass production, being a research lab. So we have done this in tens of chips for months of operation under a wide range of temperatures and voltages down to 0.3. We can actually go quite lower. So dual mode logic is actually quite better than standard CMOS at going lower voltages. It's actually more robust than CMOS logic, surprisingly, but there are reasons. I would urge you to refer to a JSSC paper that we have just published. It's not yet published in JSSC, but it's available on IEEE Explore. So there we actually show how the logic style is, the robustness, how it compares with standard CMOS logic at low voltages. So to make the answer short, we have no evidence of we have not qualified it for mass production, but based on our limited but not trivial, not narrow experience across months of testing, we have not seen a single error. Okay, so we cannot prove that this is ready to be picked up for mass production, but this gives us some confidence that this is definitely possible based on our tests. And I urge you to actually look into that paper, which is available on IEEE Explore, because it will give you a better sense of the design margins that this logic style requires. So this somewhat answers your question, but not perfectly, because we are not a company. So that is work that needs to be done by companies with volumes that are way beyond the usual interest or targets for research groups.
All right.
Thank you, Massimo. Yeah, sorry.
Can I ask?
Sure.
I have another sort of fundamental question. When you talk about uninterruptible operation, I take it to mean that you can stay on in some sense. System doesn't shut off. But when you look at applications, being on may mean some minimal performance, not just not being off. You need to accomplish at least something per second. So I'm sure that you're pushing the boundaries in everything that you're doing, but the question that remains is to take specific applications and check against the absolute requirements that they have, whether you can meet them. Communication is just one example, because energy per bit is a limit, almost a fundamental physical limit to get across a certain distance. So you may stay on at a very, very, very low rate, by which you, with a given power, achieve the energy per bit. But can you get enough bits through per second to be meaningful remains open. So again, I'm not in any way, I really appreciate everything that you're doing in pushing the envelope. I'm just wondering, if I come from the application direction, what does it really mean to me for various applications under various circumstances?
Thank you for the question. So if I understand, basically there are two questions. One is about what always on means, and the second is communications. So let me comment on the first one. So I just went back to this demo. I would actually suggest that you just go to this QR code and you just watch. It's 5 minutes, but at least you see what happens, what it does. So as you can see here, just to give you a sense, when you go from, let's say, milliwatt range, which is what a microcontroller of that scale would consume, down to nanowatt, of course, you're going to give up something. And what you give up is performance, okay? Mm-hmm. So it means that the system keeps sensing, processing, capturing events and time stamping, okay? Currently not communicating at nanowatts, okay? Mm-hmm. I will comment on communications in a minute, okay? But it's continuing to do so, okay? And by the way, when we talk about nanowatts, I would like not to be confusing. So it means that it can scale down to nanowatts. The system that I have shown adapts automatically to the level of harvested power that is instantaneously available. It mm-hmm. means that if you have 1,000 times more, you can go 1,000 times faster, and so on and so forth. So yes. The goal is to really fill the gap between the one end of the spectrum and the other end of the spectrum, okay? And doing so continuously, so that you will be able to do computation, sensing, and event detection and time stamping at the maximum speed that you are allowed to by the instantaneous conditions. So when we say always on, we mean it. Of course, whenever there is very little, let's say in this case, light, there's nothing we can do. We had to go slower. So from an application perspective, it means that if you are performing tasks that are related, let's say, to physical variables that are changing slowly, let's say environmental sensing, all applications of environmental sensing are all good. Of course, if you want to have, motion sensing, if you want to have, let's say, a wearable that tracks all your movements, so you will probably need megahertz, then you're not able to, right? So it depends on how much energy power you're getting instantaneously, okay?
Yeah, so you're basically filling the trade-off space.
Correct.
And as long as it's enough for the application, good. If it's not enough, then no. What can you do? I agree.
Okay. Yeah. The second question that you were asking was about communication. Unfortunately, I have to apologize. I cannot really talk too much about what we have done in the lab, because there is a pre-publication policy that prevents me from talking about this. And in a couple of months, I will be able to share everything, okay, with you. So it's just a promise. So let me do so.
I just meant that here too, you probably have you play between power, data rate, and range. But you're trying to exploit the maximum envelope of what's possible. It's not that you will suddenly, with a nanowatt, be able to send a gigabit per second.
No. Oh, that's for sure. That's for sure.
You're again you're giving the flexibility within the envelope of what's physically possible. This is basically
Yes.
what you're doing. So I can do the trade-off as most sensible for my application under the constraints.
That's correct.
Including in communication. Yeah, okay.
Yeah. And the philosophy is the same. So as long as the application is okay with that, the system allows tremendous scaling.
Yes. Very good. Okay. Thanks.
Thank you. We have another question.
Sure.
Oh, hi. Sorry. Here we are like at 2 a.m. in the morning, so I'm trying to stay awake.
Whoa.
Sorry. I hope that it was not too boring.
It's excellent. Yeah. So I saw the dual mode logic, and
Yes.
my question specifically is does adding the maybe the second mode to the CMOS, does that just cover the lower end of the power spectrum, or does that allow you to continuously scale down? Because when I saw your figure, I see you try to cover the nanowatt region by adding that second mode. But between the microwatt and your nanowatt, is that a region that you can also operate?
Yes. So one of the goals of the research that we started was how to fill that gap. So maybe I have been too quick, but it's not only that we can cover the two different points. So let's say minimum power and minimum energy. We can also fill the gap completely. So it's a continuous trade-off.
So through I think it's not just through say adding a second mode to the circuit, you also did some other tricks to, like you made changes to some other dimension other than
no,
the
actually it's all there. I would probably refer you to the JSSC that we published a couple of months ago on this.
Mm-hmm.
So basically, you remember that the transistors in blue and green that I showed, and I said if it's on, off.
Yes.
If you apply proper voltages at the gate of those two transistors, and you apply intermediate voltages, you're also going to achieve all intermediate, because you're going to modulate their strength, right? So you're going to move from one end to the other end continuously. That's how you get it. So the principle is exactly the same. The only difference from what I briefly mentioned is that instead of having one voltage or another, you just need to generate intermediate voltages, which is very easy. We do it with, in our test chip, we did it with a little more than 10 picowatts. So it's really nothing compared to the system. That's very easy to do.
Yeah. So maybe I'll ask a very quick second question. So
sure.
I see you're trying to your research is primarily focusing on the low power digital side. So what is the odds that let's say the big companies, for example Apple, for example Qualcomm, for example ARM, that they have developed some similar technology that's also proprietary that they have been using in their project. So as far as you know, have they been developing something similar, some ideas similar to what you are presenting here?
Well, maybe I will refrain from commenting on this, on some of our industrial collaborations and some others that are not collaborating with us. I would probably rather not comment on what they're doing. Okay. Because if I know, I'm not supposed to share, unfortunately. And if I don't know, I will tell you I don't know. But then I shouldn't differentiate anyway. So probably I will try not to answer your question just to remain, ethically sound.
Yeah, because they don't really publish papers, so we wouldn't know. Yeah, that's my question.
What I know, I can share, and what I don't know, I can share either. So it's a tricky answer to give.
Thank you.
You're welcome.
Thank you. Tsahi, do you have another question?
Yeah, I have another question. Maybe a silly one, but I'll try anyhow. especially if you have embedded memory that you can store things short-term in this case, does it make sense to time multiplex on-off on the logic as a way of scaling down performance and power on a very short-term scale? For example, instead of doing 100 hertz, kind of continuously fill the cycle, do the thing that could have operated at the kilohertz, but only every 10th cycle, 1 on, 10 off. So other than the power for switching on and off, you get linear power scaling in exchange for performance, of course. Does it make sense, or is it not as good as the things you've shown, or does it complement them?
It depends on the power mode that you are adopting and pursuing. So in general, if the limit is imposed is the peak power, so we are talking about a purely harvested mode, and this can be permanent in purely harvested systems, or could be temporary for battering different systems, right?
Yeah.
So in that case, duty cycling doesn't help at all, because it's all based on peak power. And of course, waking up actually typically increases the rush current, so it doesn't help at all.
Okay, so it doesn't help. Okay.
In other power modes where you are instead using stored energy, then the limit is the energy, not really the peak power. And in that case, you can do it, and that's it's a way to prolong the battery life. Sure.
Okay.
And by the way, I appreciate attendees like Gia who are awake at 2 a.m.
Thank you.
Any other questions, please? I guess this is it. Thank you very much, Massimo. Thank you for joining us, and we hope to see you whenever we can see each other.
Yes, I really hope to be able to visit Technion and in the area soon. Actually, as I said, it was really a plan for the last year, and then of course it didn't materialize. So hopefully life will be kind of normal soon. So we will follow up with that. And by the way, I would like to encourage all the attendees, those who have attended now or those who will see the recording, watch the recording, to contact me. If you are curious, you want to know more, just contact us. We are very happy to share what we do. We are very passionate about what we do. So the more useful it can be, the happier we are.
Thank you.
Thank you. I'm starting to get the emails with people saying thank you. And thank you once again. And thank you to all.
Thank you, Massimo.
Thank you. Hey, Hadi.
What's up?
Thanks for attending. That now that the world starts being small, right? Like as it is.
Exactly.
Good. Okay.
Yeah.
Goodbye, all. Thanks for attending again. We'll follow up through personal conversations like with Adi, or through email otherwise with anybody who is interested in what we're doing. Thank you for attending. Goodbye, all.
Goodbye.
Bye-bye. Thanks.